fragments to Earth.
It's almost like space forensics. It's like you see some television program, a crime scene, they find a piece of paint chip or a hair or some kind. Very similar to what we're trying to do.
Zhou and his colleagues designed the Stardust probe to travel over 300 million miles from Earth and collect dust grains from the comet Wild 2. There's just one problem. The dust particles will be moving up to 6 times faster than the speed of a bullet. Yet it's vital Zhou gets them back to Earth undamaged.
So what I need is special material to be able to contain the high-speed bullet. I'd be able to capture it without breaking up. So I need to capture the bullet without breaking out the bullet.
It takes Zhou over 2,000 experiments to refine his comet-catching material. It's made of the same chemical as glass, silicon dioxide, only 1,000 times less dense. Zhou calls it smooth gradient silica aerogel. If anything can stop comet grains, it's this stuff. With aerogel capture cells on board, the probe is good to launch. On February 7th, 1999, it blasts off atop a Delta rocket.
We have main engine start and liftoff of the Stardust spacecraft, returning a time capsule with the elements of the formation of our solar system.
Its 2 billion-mile journey takes nearly 5 years, but eventually, the night of the comet encounter arrives. At Mission Control, all Zhou and his colleagues can do is wait.
We had done many simulations, but still the questions, will it run into a comet? Even if it doesn't run into a comet, did it collect dust at all? It would be horrible when it comes back and no dust.
Finally, in 2006, the capsule re-enters Earth's atmosphere. It makes a safe landing, and scientists rush its precious cargo to the lab. As soon as they open it, they know the mission is a success.
If I capture one particle that I can see with the naked eye without a microscope, I will be pleased. But I caught more than 3 dozen of them.
It's an incredible achievement. These are the first pristine comet particles ever to arrive on Earth. The grains may be tiny, but they contain a wealth of information.
It will take many years really to understand the formation of the solar system. It will take probably a couple of decades to milk all we can from the Stardust samples.
The team may have to wait decades for all the results. But in the meantime, others are trying a different approach. Comets aren't the only source of material from the early solar system. Meteorites are ancient too, and they have one huge advantage. They come to us.
The amazing thing is that any time you pick up a meteorite, with very few exceptions, you take it into the laboratory, you date it, the answer is it's 4.5 billion years old. 4.5 billion years old. These are pieces of the early solar system. And so here you have in your hand a piece of something very substantial that connects you and connects our existence and connects the history that brought us to be with this larger universe.
After extensive analysis, Hester's team discover unstable isotopes of iron-60 locked inside the meteorites. It's totally unexpected. Iron-60 decays relatively fast, so it must have come from close by. If it came from any great distance, it would have had time to decay into a different isotope before the meteorite could trap it. Only a supernova can make iron-60, so there must have been an active supernova close to the infant sun.
To come along with a piece of hard evidence that says that nope, early sun, early solar system, were in a violent environment near a massive star, experienced a nearby supernova, it was surprising. We realized that this is going to change the way that people think about what goes on. This is going to change our understanding of the origins of the solar system.
Despite the violent forces being unleashed, our solar system may have formed right alongside a supernova.
These are exquisitely violent events, and they reshape everything around them.
Shock waves from exploding supernovae pummel everything within 20 light years. A galactic bomb blast. What's astonishing is that all that destructive force may have been exactly what was needed. Blast waves can push dispersed matter together, like a broom sweeping up dust. So the collapse of our giant cloud of dust may have been triggered by the blast from the nearby supernova.
They'll send shock waves and compress the gas for light years around them, and that compression triggers the birth of other stars.
The blast wave could have swept together the material of our nebula. When compressed enough, gravity would start to have an effect, and the cloud would begin to collapse. Within the cloud, swirling about the infant sun, the planets are beginning to take shape. And today, scientists are beginning to understand the astonishing processes that form them. For years, the process of planetary formation has puzzled scientists. Some astronomers now believe planets grow within the disk of gas particles surrounding a newborn sun. But this material is spread too thin for gravity to pull it into clumps. Then in 2003, some informal experiments on board the International Space Station shed some light on this long-standing mystery. Astronaut Don Pettit spends his free time in space messing around with a few experiments to see how particles behave in zero gravity. He takes different grains, such as coffee, sugar, and salt, places them in pouches, and watches as they begin to attach to each other. He realizes that the friction between them as they rub together inside the pouches is creating an electrostatic charge that pulls particles together and forms them into clumps. The same electrostatic charges would have been created if the experiment were carried out on Earth. But on Earth, the far stronger force of gravity would have made it impossible to observe the same results. Pettit and his colleagues realize that what they are seeing in the zero-gravity conditions of the space station would also have occurred in the zero-gravity environment of the early solar system. The particles in the protoplanetary disk may somehow get charged and attract each other. It's a process known to planetary scientists, such as Jack Lissauer, as accretion.
We see signs of accretion in our daily lives. Raindrops condensed as very, very tiny droplets around small little pieces of dust, and they collide with one another as they fall in much the same way that grains collide in the solar nebula and accrete into bigger objects.
Once the clumps reach the size of mountains, they exert a significant gravitational force. It's more powerful than the electrostatic force, so the whole process accelerates fast. In about 1 million years, the clumps can grow into larger planetesimals, or pieces of planets, and can keep on growing into full-size planets. Gravity keeps these planets locked into their orbits around the sun, traditionally understood as a mysterious pulling force. Since Einstein, scientists have a new understanding of gravity.
Most people know that it's the sun's gravity that keeps planets moving in orbits around the sun. What we're going to do here is we're going to take a little bit deeper look at what the nature of gravity really is. Now, Newton's first law of motion, law of inertia, says that an object moving in a straight line at a constant speed will keep doing so. So here in the overhead view, we're looking down at a flat surface, and if I take this ball, which represents a planet, and I roll it across the surface, and sure enough, it moves in a straight line at a constant speed. Now, Einstein said there's actually more to it than that. Einstein said that if you took a mass, for example, the mass of the sun, represented here by this plunger, that mass had the effect of distorting the shape of space-time. Now, to us, it doesn't look distorted. If you look on the overhead shot, it still looks as flat as it did before, just like a chessboard, but in fact, it is distorted. And so now when I take my planet and I move it through this distorted space-time, it tries to follow a straight line, but there's no straight line available for it to follow. And so instead what it winds up doing is it winds up moving around the central object on an orbit. It's that effect of that curved space-time that we usually call gravity.
Gravity exerts an equal force in every direction, so its effect is always to attract matter evenly toward the center of a body. Therefore, when it's strong enough, gravity will resculpt any body into a sphere. This is why all planets in the solar system form nearly perfect spheres. With a diameter of over 300 miles, no other shape is possible. All the planets are roughly spherical, and all come from the same original disk, but they end up as radically different worlds, from rocky Mars to gassy Jupiter. The differences are primarily down to one basic law of physics. Different kinds of material condense at different temperatures.
It has to do with, given a given temperature, what is a gas and what is a solid, and that's it.
At first, all the matter around our young star is so hot, it's in a gaseous form. Then, further out as things cool, material begins to condense out of the cloud, like snowflakes forming on Earth. In the inner solar system, closest to the sun, it stays hot.